Hi, everybody. It's quite an honor. We have our special speaker today, and to introduce us about advanced manufacturing in Massachusetts. And she is Dr. Anu Agarwal from MIT. And let's just let her introduce her program, her research, and her thoughts about the education pipeline and the workforce development in Massachusetts, especially in advanced manufacturing. Dr. Anu, please.
Thank you. Thank you so much, Dr. Justin. I appreciate it. We can see my screen. So my name is Anu Agarwal, and I'm a principal research scientist at the MIT's Initiative for Knowledge and Innovation in Manufacturing, also called IKIM, also Materials Research Lab. And I'm a part of AIM Photonics Institute, one of the manufacturing USA institutes in the country. So I'm just going to quickly talk to you about integrated photonics and the workforce development that we're doing in the space of manufacturing within integrated photonics topic, and how we're building a strategic curriculum for ongoing self-paced skilling, or what we also call agile continuous education, through the definition from the Office of Open Learning at MIT. So microelectronics education and workforce development, let's just go through a few of the myths and facts. We're wondering if there's a glorious past that existed here within USA, within Massachusetts, that has been lost, and we're gaining it back now. First of all, there has been no correlation between skills and pay for entry-level workers in the field of manufacturing, and there has been no standard workforce pipeline into manufacturing. Also, the Massachusetts workforce is aging, and they need to be replaced, or skills will be lost. Most companies know what skills are needed at the entry level, and also how can we use latent competencies within the state and within the country to build up on it and reshore manufacturing, specifically advanced manufacturing. So the infrastructure that we have for future leadership is supply chain readiness, the chips, the packaging, the printed circuit boards, all of them. Technology roadmaps are very helpful because they give guidance for investments. And Massachusetts specifically has 28 agencies that address all aspects of EWD and has a history of electronics manufacturing. Can we revive this through leadership? And here's the product portfolio of the Initiative for Knowledge and Innovation in Manufacturing, or IKIM, at MIT. As I said, we'd like to prepare the advanced manufacturing workforce using agile continuous education, which means we deal with students, learners across the entire human capital chain, or the human supply chain, all the way from K through 12 to community college, to undergrad, to graduate, to incumbent company employees. So we try to provide education through which we develop the workforce, and we try to provide a roadmap for those who are in the community to see what's coming next, 5 years, 10 years, and maybe even 20 years down the road. So we'll go through a few of these different products that we offer in order to build the workforce development within the state. And perhaps this model can be extended across the country. So in education, we have summer academies, online education, including manufacturingworkforce.org, which is a new open edX platform set up by DOE, virtual lab with virtual reality-based teaching simulations that help to build intuition and get concepts right all the way at the beginning, the foundational level. TED-Ed videos, which are very popular among our younger audiences, short courses, teaching packages. Also, we offer boot camps at what we call the Labs for Education and Application Prototypes, or the LEAPs, of which there are 5 in the state. I'll talk more about that. Training students and teachers are very important. We call it train the trainer when we teach the teacher. Certification, internships. And then we also work closely with our community college partners in problem-based learning module creation. So we try and build this nexus of government, community college, university, and industry partnerships, and try and build this whole infrastructure of trying to get STEM education expanded across the board. In the roadmap part, we have technical meetings. We do both technology roadmaps and educational roadmaps, and we offer webinars. So all of this product portfolio is for blended learning, both on-site and online, and can be used for workforce skilling, reskilling, and upskilling. So this is our EWD idea as we go forward. We need to build up manufacturing, but we have to start with education and workforce development. So focusing on the online education, we have certain flagship courses, for example, PIC Design, that we offer online through MITx and our Open edX platform, manufacturingworkforce.org. So this particular course, the Photonic Integrated Circuits one, is led by Professor Stephen Treble at Rochester Institute of Technology, and helped by a lot of other faculty, including Professor Jaime Cardenas at University of Rochester, Alan Faust at University of Arizona, Eric Verlarge here in MIT, Professor Kimmerling, and Greg Howland. So it turns out that this course is popular. We have almost 2,000 registrants, and each of these registrants, these learners, they learn about the material, and they also send in designs that are fabricated at the AIM Foundry. And then a few of them can come in to test it. So it's the entire pipeline. You learn how to, you learn the subject, you learn the concepts, you make the design, you fabricate it, and you test it. So this is a very popular online course that we offer, which is actually ongoing right now. We offer other online courses as well through our Open edX platform, interactive virtual manufacturing lab design, photonic integrated circuit testing, as well as photonic integrated circuit sensors, manufacturing cost and environmental impacts, fundamentals in advanced device design. So all of our faculty from across several universities are brought on board along with industry partners to teach this material that will train people on the next generation that's required for advanced manufacturing. Moving on to the workforce development part, the boot camps and the training of students and teachers, we use the three-legged stool approach to education and workforce development. The three-legged stool is the lecture, the virtual reality simulation, not just tool, but also device simulation, and hands-on experiments. So lecture, virtual reality, and hands-on. We follow this model, and we find that it's very effective in training our learners, not just good for the learners, but also good for the teachers, this model. So the model includes lectures, both online and in person. We usually have, for example, we try to include guest lectures as well in our training for the advanced manufacturing, because companies can then be involved and train learners in what's required to come and work for that company and move things into products, not just about content and academic knowledge. Simulations, they're excellent both for device and tool simulations. We have heard constantly that it has diminished the overwhelming majority of cases. It has diminished the factor of cognitive load in learners as well as in teachers. And this has been very helpful when we've included it in our program. Laboratory experiments, I'll talk specifically about the die bonder, which is a tool that is used for packaging of electronic and photonic chips, but it's a complicated tool. And necessarily, tools that are used in chip manufacturing are complicated. So we try to simplify it by using virtual reality simulations such that you can train on the tool 85% already before you even set foot in the laboratory. So you know what to expect when you come into the lab. So three-legged stool approach, lecture, simulation, and labs. And we also offer teaching packages, including chips that are manufactured at the AIM foundry. This hands-on photonics education, or HOPE, as we call it, is led by Professor Stefan Prebel at RIT. And we've designed multiple chips. Now we're in the process of designing further chips that are geared towards certain applications, such as datacom chips or RF chips or sensor chips. But we already have designed a generic chip, as you can see on the left-hand side. It has 3 chiplets in it, and it includes all kinds of photonic devices that can be tested, and learners can learn about device functionality. And on the right side, these are the 6 datacom chips that we're putting out. We have the next generation now. We talk about insertion loss. We talk about the different devices used in datacom telecom, including directional couplers, Mach-Zehnder interferometers, tuning, as well as modulators and photodetectors, and so on. So these are the kind of teaching packages that we, in conjunction, the university partners, in conjunction with AIM Foundry, are putting out there for training of the next generation. And we include manuals, detailed manuals, as well as tools that are required. So people can take these chips, use our manuals, and get started in their own labs right away to train their students. Now, the LEAPs through which we are training students within Massachusetts is an excellent network of labs that was established by the Commonwealth, by the state of Massachusetts. There are 5 of them spread across the state, as you can see. Western New England University, Worcester Polytechnic and Quincy Government Community College, Stonehill College, Bridgewater State University, and MIT. And each one of these LEAPs has around it several community colleges that it can serve in conjunction with industry partners that are geographically close to those community colleges. So they can be employing the graduates of these programs that come out of the LEAPs. So the LEAPs are an excellent way to have geographically diverse regional centers of excellence, so to speak, to train students both in university level and community college level, as well as high school level, locally, and then bring them out to companies. So this is our way of spreading STEM skilling across the state, and this model of LEAPs can be applied across the country as well. We offered recently an integrated photonics bootcamp between MIT and Bridgewater State University LEAPs, in which we taught about chip packaging and chip testing. We had several students who are undergrads, grads, company folks come in and learn about, in this case, packaging and testing. And in packaging, we focus on the die bonder, which I said before was one of our flagships. We're trying to bring in virtual reality for tool training, and this is the first one that we're introducing. So the virtual manufacturing lab, let me say a little bit about that and how we use it to educate. It's in collaboration with Educate Workforce at Clemson University. And what we provide are modeling and design tools at the device level, as you can see up on the top, which shows you how waves, electromagnetic waves, propagate within structures on a chip. And those structures can be simple waveguides, or they can be ring resonators, as are shown on the right side. So these build concepts are understood clearly by learners. What is happening to this electromagnetic wave as it travels through the waveguide? Another thing that we do is, am I froze? Oh, here. So another thing that we do is tool training using virtual reality simulations. You can see here is shown a fiber lathe, a draw tower that is being simulated virtually through guided practice and an open exercise. We'll talk about how we are using this idea for die bonder tools. And finally, the application-based educational games that are shown down below here for datacom telecom on the left side and for sensor systems. So game-based learning is a very popular way of teaching difficult concepts. And this is what the Virtual Manufacturing Lab at MIT is attempting to do. So modeling and design through fundamental training, tool training, and game-based training. In terms of tool-based training, we have our lab tool. Here I show you the MRSI M3 die bonder. They're a good partner of ours. They make the pick and place tool. They're local. And their tool is complicated to use, as are all die bonders, because this is a very difficult task to perform in packaging. What we have done, as you can see below, is we've created a virtual reality simulation, which is on a desktop. You can use it with virtual reality glasses, but we think that it's much more ubiquitously used when on a browser. So here below, you see a desktop virtual reality simulation of this complicated die bonder tool. And on the right side is a simplified version of the software. Exactly what do I need to know that the software will do in order to pick and place a chip onto a substrate? Now, all of the other complicated parts can be learned as well. Don't get me wrong. It's not like we're throwing that information away. We're introducing the learner step by step and building complexity as we go along. So that was about the boot camps and the LEAPs. We also offer certification, internship, and partner with community colleges. We work with Stonehill College, for example, as well as Massachusetts State through the MassBridge program. And this trains across multiple US manufacturing institutes. We start with the fundamentals across the board in manufacturing. What knowledge is required? And those we call the manufacturing foundational training. We build up into other courses that are much more specific. And finally, we reach the high level of specialization for either AIM Photonics or robotics or NextFlex, fibers into a FOA, America Makes, or LISP. So this is the idea. Start basic, which are standard common courses, and then build up to specialization through a pyramid-like approach. And this is through the MassBridge, this technician training program for the workforce of the future. We partnered, MIT partnered with AIM Photonics, with ARM, Stonehill College, Bridgewater, and Westmoreland County Community College. So this is that pyramid: foundational course, industry-wide manufacturing, and up to the institute-specific course. It was actually implemented here in Massachusetts, and it was a 15-month technician certification program. It was so successful that the students who came from across different backgrounds, some of them without even STEM training initially, they ended up with jobs in the local industry, STEM jobs in local industries. And now we're on the third cohort of this whole group run by Stonehill College. Extremely successful program. And here is a picture of some of the students, the graduates of this program. And we're continuing on through Stonehill College. Started with this seed between a communication of MIT and Stonehill and Bridgewater, and now taken forward by Stonehill. We also do problem-based learning through our partners. For example, MIT has worked with Springfield Technical Community College, specifically Professor Nick Massa and his team, to develop problem-based learning. So we define the problem, as you can see on the left here, In this case, it was a sensor, PIC sensor. How can you design a sensing element on chip that can be very sensitive? That means it has a long path length of interaction with the analyte, but has a small footprint. So how can we do that? Well, they had to come up with a solution that you can have either a paper clip or a spiral structure that has a large waveguide, but a small footprint. So this is what they came up with. They have a problem-solving whiteboard that has been set up for them in their own university, in their own college, where you define the problem. What is the criteria for successful solution? What do we know? What do we need to learn further? And what assumptions are we making? Who will work on what? So you distribute the workload among a team of students within the community college, and then come up with solutions, brainstorm. What are the potential solutions? What solution will we come up with? What have we settled on? And then we validate that solution. And finally, we compare that with what the solution was provided by students at MIT who faced this challenge in their research. So we test it, and then we compare it with what's out. This is how we've been working with the community college on problem-based. And this is very, very essential for building STEM skilling within manufacturing. So they came up with a proposed solution, which was a spiral, and exactly as our graduate student had also worked. So it was a very nice sort of merging of interest between community colleges and MIT. Then moving on to the roadmaps, we have technical meetings. We do both technology and education roadmaps. The Summer Academy helps us to get this going. For example, we offer a week-long training of different topics, and they end each day in challenging problems that are solved in each of the application areas. For example, there may be a challenge problem for datacom telecom, one for RF photonics, one for sensing, and one for LiDAR imaging. Each of the tracks, they end in a certain challenge problem that students pick up and work on at the end of the day. And on the end, Friday of this week-long training, they present what they come up with as a solution to this design. So it's a very interesting combination of faculty and industry. We have vendors of EPDA tools actually participating in teaching students how to build process design kits. The technical meetings, which are roadmap meetings, are held spring and fall. Recently in June, we had one in MIT. The fall one is going to be held in the Netherlands. It's an international technology roadmap session. And in the education side of it, we looked at industry workforce needs. So Dr. Sajjan Singh and Professor Randy Kirchain interviewed people in industry and asked them, what exactly are you looking for in people who you wish to hire? And they created this entire map that says what is needed. What is needed, they found, is more cross-training among PhDs, interdisciplinary training. So material science, electrical engineering, mechanical engineering, all of these have to come together, and students need a little bit more interdisciplinary and training in design for manufacturing, design for test, design for packaging. So the DF part is very important. And also supply chain analysis. So we needed to get input from industry and then build curriculum based on what industry needs to advance manufacturing. So this partnership between industry and academia across the board, from kindergarten through 12th, community college and universities, as well as in all of these have to work together to build the next generation. So the industry recommendations were we need to train people in design for manufacturing, for packaging and testing. Case-based courses, case study-based courses would be very helpful. Application to understand drivers and trade-offs and fundamentals. So these are the recommendations for the AIM Academy training priorities based on what industry suggested. And we need to improve this pipeline for domestic PhDs. We need to make sure to understand why are they not selecting photonics study. They may be selecting other STEM, for example, physics, engineering, math, computer science, but a certain manufacturing area, say photonics, say fiber manufacturing, say flexible electronics. Why, if they're not selecting it, why are they not selecting it? And we have to understand this pipeline. What drives the field of study? When does this decision happen in a learner's career? And what fields are being selected over and above those fields that I just mentioned? So we have to think about improving this pipeline for domestic training, all the way from K through 12 to PhDs. And I'll end with our core team. This is Professor Lionel Kimmerling, Dr. Sajan Saini, myself, Anu Agarwal, Dr. Eric Verlage, Dr. Pradnya Nagarkar, Dr. Jürgen Michal, Professor Jiwajin Hu, Dr. Randy Kershin, and Professor Samuel Cerna. So back to you, Dr. Kaufman.
Thank you, Dr. Anu. This is a great information and learning about the whole pipeline from like education to workforce development, and understand like, oh, what's happening in advanced manufacturing and how you design the courses, the short course, and even the internship, mentorship, the internship and the mentorship. So I have a question for you here. So as a woman in STEM field, and can you share some thoughts, or you may have several conversations with the different groups, like some insight about women in advanced manufacturing area?
Oh, sure. I actually thought about this and I prepared a slide. Can I just show my slide?
Excellent. Yeah.
Okay, there we go. So women in STEM manufacturing, we have to start right at the K through 12 level, as I mentioned. Students and teachers train the trainers. And right now, such programs are being conducted through Western New England and Worcester Polytechnic Institute Lab for Education and Application Prototypes. We at MIT are doing some of this work. Bridgewater State University, I know they go through training students in middle schools, especially Professor Samuel Cerna, who's an Optica ambassador. He has been doing a great deal of that work. So we have started remembering there's also Spark Photonics. Dr. Kevin McComber within the state of Massachusetts has been working closely with our LEAPs and helping to bring the energy and excitement of manufacturing into the lower grades. So Keys at MIT is another program. It's for middle school girls, and it's run by the MIT Society for Women Engineering. Girls Who Code is an overall program that enables young girls to, inspires them to come into the field of coding and programming. And a recent statistic shows that 40% of undergraduate population at MIT is women. Starting off with 1, 2, 5%, it's reached 40%. So that's excellent. Also, NSF has some very good strategic goals for diversity, equity, inclusion, and accessibility. Their DEI goals are spanning all of the proposals that they're asking for. And this is an excellent way to bring women into STEM manufacturing. We at the IKIM, per se, we're working with several women in educational roles for STEM manufacturing within the state LEAPs and community colleges. And here's just a few examples. For example, in Mass Bay Community College, we work with the faculty and dean there, Professors Marina Bograd, Professor Chitra Javekar. We work with Stonehill College, Professor Ruby Blue and Professor Cheryl Fulzer. We also work with Bridgewater State University, Professor Elif Demirbass. These are just few examples of women in STEM manufacturing who we are working with from the Initiative for Knowledge and Innovation in Manufacturing through the LEAPs. And then women in STEM industry, there are many of them. There are several startups and established companies with women in leadership roles. And of course, there are many women in the advanced USA manufacturing industry. So I'd like to encourage and inspire more and more women to join STEM manufacturing within the state, within the country, and actually globally.
Yeah, this is really exciting. Like, thank you for letting us know so many excellent examples and like a community practice from higher education, from the private sectors, community college, and the research center really work together to kind of enhance the advanced manufacturing. So hope like you really use this chance that more and more girls and then can join this pipeline and pathway to contribute their career in advanced manufacturing.
Thank you, Dr. Kaufman. I really appreciate this opportunity. It's a topic close to my heart, very interested in bringing up STEM across the board. You know, how can we get more and more people to enjoy STEM and contribute in a meaningful way through their professional careers?
Exactly, absolutely. Thank you so much for your time and this chance let us know more and learn more about this area, STEM field, advanced manufacturing. Thank you.
Thank you.